Hi, this is Schwartz from MasterMathMentor.com. This is video AB12b. The topic is transcendental functions, and this covers the AB manual pages 60 and 61. Let's start by trying to take the derivative of e to the x. It seems that this function does not fit any of the established formats: power, product, quotient, trig, natural log. It's not a power form because that form is x to a power. So let's have the calculator compute the derivative for us. We will let y1 equal to e raised to the x and y2 equal to n deriv of e raised to the x, comma x at x. On page 60 there is a table for e to the x and the derivative of e to the x. So turn off the video and complete the table. It should be obvious by our table that the derivative of e to the x is e to the x. How cool is that? But how do we go about proving it? There's a technique in calculus called logarithmic differentiation. It's not part of the AP exam, but we can understand it. We start with y equals e to the x as our original function. In logarithmic differentiation, we take the natural log of both sides. So we get the natural log of y is equal to the natural log of e to the x. But we realize that the natural log of e to the x is the same thing as x natural log of e using your log rules. So we have natural log of y equals x natural log of e. But natural log of e is defined as 1. So we have the statement that natural log of y is equal to x. So now we perform implicit differentiation. We get 1 over y dy dx is equal to 1. And cross multiplying, we get dy dx is equal to y. But y is e to the x. So we approve that dy dx is equal to e to the x. So we have our next rule that says that the derivative of e to the x is e to the x. And if u is a differentiable function of x, then the derivative with respect to x of e to the u is e to the u du dx by the chain rule. It should also be noted that the derivative of c e to the x, where c is a constant, is c e to the x. So c e to the x is the only function whose derivative is the same as itself, other than y equals 0. In problems 19 through 22, you are given expressions involving e to a power, and you're asked to find the derivative. In 19, you're given y equals e to the 5x, so the derivative is e to the 5x times the derivative of 5x, which is 5. Final answer, 5e to the 5x. In 20, y equals 4e to the 1 minus 2x, so the derivative is 4e to the 1 minus 2x times the derivative of 1 minus 2x, which is negative 2. Final answer, negative 8e to the 1 minus 2x. 21, y equals e to the 1 over x. So the derivative is e to the 1 over x times the derivative of 1 over x, which is negative 1 over x squared. Final answer, negative e to the 1 over x divided by x squared. And finally, 22, y equals 2e to the square root of x. The derivative is 2e to the square root of x times the derivative of the square root of x, which is 1 over 2 square root of x. The 2's cancel. Final answer, e to the square root of x over the square root of x. In calculus, exponential expressions are usually written as e to some power, but occasionally we will have expressions in the form of a to x, where a is a constant. So the derivative of a to the x turns out to be a to the x times the natural log of a. And if u is a differentiable function of x, then the derivative of a to the u is a to the u natural log of a du dx. There are three pieces to that answer. In problems 23 through 26, you are given equations in the form of some constant to a power and are asked to find the derivative using the rule above. In 23, you are given y equals 2 to the x, and the derivative is 2 to the x, natural log of 2. In 24, you're given y is equal to 5 to the 3x plus 1. The derivative has three pieces to it. 5 to the 3x plus 1 times 3 times the natural log of 5. 25 is the same. Y equals 6 to the x squared plus 2x minus 1. So we'll need in our answer a 6 to the x squared plus 2x minus 1. We will need a 2x plus 2, and we'll also need a natural log of 6. And in 26, we have y equals 1/4 to the x, and therefore the derivative is 1/4 raised to the x times the natural log of 1/4. And the natural log of 1/4 can be written as the natural log of 1 minus the natural log of 4, and the natural log of 4 is 2 natural log of 2. We can also take the 1/4 to the x and write that as 1/4 to the x. So our final answer is negative natural log of 4 over 4 to the x, or negative 2 natural log of 2 over 4 to the x. As of now, these are the derivative forms and rules that you need to know for AP Calculus. Later in the course, we'll learn several more involving inverse trig functions. But for right now, this is it. You need to make sure that these rules are part of you. For all these rules, we assume that u is a differentiable function of x. Our first three rules are the algebraic rules: the power, the product, and the quotient. So the power rule says that the derivative with respect to x of u to the n is n u to the n minus 1 times du dx. The product rule states that the derivative with respect to x of f of u times g of u is f of u g prime of u plus g of u f prime of u times du dx. And finally, the quotient rule states that the derivative with respect to x of f of u over g of u is a fraction where the denominator is g of u quantity squared, and the numerator is g of u f prime of u minus f of u g prime of u multiplied by du dx. One note about the quotient rule. When performing this rule, the numerator is frequently complicated, and students can get so immersed in the numerator that they forget the denominator. That's why I like to write the fraction line first and immediately square the denominator, and then work on the numerator. In that way, I will not forget the denominator. Our next rules are the Six Trig Rules. The derivative with respect to x of sine of u is cosine of u du dx. The derivative with respect to x of cosine of u is negative sine u du dx. And the derivative with respect to x of tangent u is secant squared u du dx. The next three are not used as much, but they still must be memorized. The derivative with respect to x of cosecant u is negative cosecant u cotangent u du dx. The derivative with respect to x of secant u is secant u tangent u du dx, and the derivative with respect to x of cotangent u is negative cosecant squared u du dx. Again, a good way to memorize these is that the derivative of any trig function beginning with the letter c is negative. Finally, we have our rules for our transcendental functions. First, the natural log rule that states that the derivative with respect to x of the natural log of u is 1 over u du dx. Our e rule says that the derivative with respect to x of e to the u is e to the u du dx. And our a rule states that the derivative with respect to x of a to the u is a to the u natural log of a du dx. On page 61, problems 27 through 34 have 8 equations, each containing e. You are to take the derivative of each. Turn the video off and first decide the rule, remembering that just because there is an e in the equation does not mean it is an e rule. Then actually take the derivative. 27 reads quantity e to the x plus 3 quantity cubed. This is a power rule. So we have 3 quantity e to the x plus 3 quantity squared times the derivative of e to the x plus 3, which is e to the x. Final answer, 3 e to the x quantity e to the x plus 3 quantity squared. 28 is a simple product rule. So we have y prime equals x times e to the x plus e to the x times 1. 29 is a trig rule. We are taking the sign of an expression. So we have cosine of e to the x times the derivative of e to the x, which is e to the x. 30 is an e rule. Y equals e to the sine of x. So the derivative of e to the sine of x is e to the sine of x times the derivative of sine of x, which is cosine x. 31 reads y equals natural log of x plus e to the x. This is an ln problem. So the derivative of an ln is 1 over the expression times the derivative of the expression. And therefore y prime is equal to 1 plus e to the x over x plus e to the x. 32, y equals e to the 4x over x is a quotient rule. We first square the bottom, and the numerator will be x times the derivative of e to the 4x, which is 4e to the 4x, minus the numerator e to the 4x times 1. Final answer, 4x e to the 4x minus e to the 4x over x squared. 33 is also a quotient rule, y equals x over e to the 4x. First step is to square the bottom, and we get e to the 8x. And the numerator will be e to the 4x times 1 minus x times the derivative of e to the 4x, which is 4e to the 4x. In this problem, I chose to factor out the e to the 4x upstairs and get e to the 4x times the quantity 1 minus 4x over e to the 8x. I did that so we could do some cancellation, and we end up with 1 minus 4x over e to the 4x. 34 reads y is equal to the cube root of e to the x. We can rewrite that as y equals e to the x over 3, and this becomes an e problem. So the derivative of e to the x over 3 is e to the x over 3 times 1/3. Problems 35 and 36 are also derivative problems, but they are a little bit more complicated. Again, turn off the video, determine the rule to take the derivative, and then actually take it. 35 reads y equals x to the 10th times 10 to the x squared. This is a product rule. So we have the first expression, x to the 10th, times the derivative of the second expression, which is 10x to the second, natural log of 10 times 2x, plus the second expression, 10 to the x squared, times the derivative of the first expression, 10x to the 9th. So we get 2x to the 11th times 10 to the x squared times natural log of 10 plus 10x to the 9th times 10 to the x squared. We can do some factoring here. We can pull out a 2x to the 9th, 10 to the x squared, and multiply that by x squared, natural log of 10, plus 5. 36 reads y equals secant squared of the natural log of 4x squared plus 2. If you got this problem right, you really understand derivative rules and the chain rule. Our first step is to rewrite it as y is equal to secant of the natural log of 4x squared plus 2 squared. This is a power rule, so the 2 comes in front, and we write the expression secant of the natural log of 4x squared plus 2 to the first power. But then we have to multiply that by the derivative of the secant of the natural log of 4x squared plus 2. The derivative of secant is secant tangent. So we attach the secant of the natural log of 4x squared plus 2, tangent of the natural log of 4x plus 2, and we're not done. We then have to multiply that by the derivative of the natural log of 4x squared plus 2, which is 1 over 4x squared plus 2 times 8x. Since we have the secant of the natural log of 4x squared plus 2 written twice, we can write this as 2 secant squared of natural log of 4x squared plus 2 times the tangent of the natural log of 4x squared plus 2 times 8x over 4x squared plus 2. And putting it all together, we end up with 8x over 2x squared plus 1, secant squared of the natural log of 4x squared plus 2, tangent of the natural log of 4x squared plus 2. On a problem this complicated, it should be noted that the use of parentheses and brackets make the problem a lot easier, particularly the use of the chain rule. It is highly recommended. 37 gives an equation, x e to the y plus 8x minus 3 natural log of y equals 0. We want to find dy dx. There's no way we will do this problem explicitly, as solving for y is next to impossible. So we do it implicitly. X e to the y is a product, and we get x times e to the y dy dx plus e to the y plus 8 minus 3 times 1 over y dy dx is equal to 0. Multiplying everything by y, we get xy e to the y dy dx plus y e to the y plus 8y minus 3 dy dx equals 0. And we're left with dy dx is equal to y e to the y plus 8y over 3 minus xy e to the y. 38 reads f of x equals e to the x minus e to the negative x, and you're asked to find the 20th derivative of f of x. When you're asked to find the 20th derivative, you're not going to spend the time finding the first derivative and the second derivative and the third derivative, etc. There must be an easier way. We take f prime of x and we get e to the x minus e to the negative x times negative 1, which is e to the x plus e to the negative x. The second derivative is e to the x plus e to the negative x times negative 1, which is e to the x minus e to the negative x. And we're right back to where we started. So every even derivative gives e to the x minus e to the negative x, and the 20th derivative is e to the x minus e to the negative x. At this point in the course, you may not be super impressed with calculus. It seems to be a lot of rules and algebra with no real reason for it other than this obscure slope of the tangent line concept. Rest assured this is not true. Similar to building your vocabulary before you start reading books, our approach is to put out the rules first for calculus and get you to understand and use them, rather than having to backtrack and learn them when we actually see applications. Our derivative rules are mostly over, and pretty soon we can start to see how they are used.